This is a standard rates question. And in this, you're provided with concentration values, and you are to see how the change in concentrations of each of the reactants affects the rate of the reaction. So in this question, you're being asked, you've got the overall equation here. They're not asking about the mechanism of the equation, but that could be in future questions we can have a look at. But today is just focusing in determining the order of reaction. Now, in here, if we have a look at questions 1 and 2 are good to compare. You see questions in experiments 1 and 2, the concentrations of BrO minus and H plus remain constant, so we can disregard them. But you can see that the concentration of Br minus increases by 3. Now, you can also see that, so it's multiplied by 3, and here we want to see that this increases by 3 to the power of x. We don't know what that x is, that unknown. So 7.56 to the power of minus 4 divided by 2.52 times 10 to the minus 4. This gives you 3. So this is actually a first order with respect to Br minus. So we could word it something like, as the concentration of Br minus is multiplied by 3, rate also is multiplied by 3. So it is first order with respect to Br minus. First order. Now we are to do this for the next, so for Br, what would be good ones to compare for? Let's compare experiments 3 and 4. In experiments 3 and 4, so we look at this one and this one. You can see again that the concentration of BrO3 minus is kept the same. Now, there's a bit of a tricky thing here. What's happening is that the concentration of Br minus is halving. So let's multiply that by a half. The concentration of H is also, actually it's not halving. What's happening here? (0.08 and 0.1). Okay, let's see what's going on here. So from there to there, yeah, 5. This is multiplying by 5. So the effect on the rate is going to be, we can multiply it by half because it's first order with respect to Br minus, multiply it by half, and then it's going to be multiplied by 5 to the power of something. We don't know what that unknown is yet. So what we do, 2.52 times 10 to the minus 4 multiplied by a half, and then we're going to multiply by 5 . That doesn't seem to give you the right answer. So let's times by 5 squared. Wait a minute. 2.52 times 10 to the minus 4 let's times that by half, and then multiply that by 5 squared. So let's see, is it second order? And yes, it is. It is second order. So we can word it as the concentration of H plus is multiplied by 0.5 and, sorry, not 0.5. When the concentration of H plus is multiplied by 5 and Br minus is multiplied by 0.5, rate is multiplied by 12.5. Where's the 12.5 come from? Half times 5 squared, which is 25 times a half. So it is second order with respect to H plus. And for BrO3 minus, to determine the order of reaction, I'm thinking we will use experiments. Something peculiar is going on here. If I just highlight to you, you see actually the rate is not changed in experiments 1 and 3 because you are doubling the rate here, but you are, this is where it starts to get a little bit tricky. Which experiments shall we compare? Which will be straightforward to determine BrO3 minus? Let's do, okay, let's do experiments 1 and 4. 1 and 4. So 1 and 4. Why are we going to do 1 and 4? Because this concentration is the same, so we can disregard that. The concentration of H plus is being multiplied by 5 again. From there to there, it's being multiplied by 5. And from there to there, what's happening there? Is being multiplied by a half. So what's happening is the rate, this rate, it should be multiplied by use a different color. So that rate should be multiplied by 5 squared and also half to the power of x. We don't know what that x is. So let's try this. 2.52 multiplied by 5 squared, 2.52 to the power of minus 4, don't forget the powers, multiplied by 5 squared, and then multiply that. Let's check if it's first order. Let's just multiply it by another half. Yep, and we get the answer. We get the same answer. So it turns out that this x here but this x here is to the power of 1. So how would we word that? As the concentration of BrO3 minus is multiplied by 0.5 and H plus is multiplied by 5. The rate is increasing again by 12.5. And from there, we can deduce that it is first order with respect to BrO3 minus. Let's see the mark scheme. So let's see. First order with respect to Br minus, yep, that's correct. Second order, H plus, that's correct. And first order to BrO3 minus, good. So from here, it wants us to determine the rate equation. And from here, the rate equation will be K, what we got here, Br minus, H plus, and BrO3 minus. Br minus is first order, H plus is second order, and BrO3 minus is first order. Ladies and gentlemen, you have your rate equation here, and it wants you to work out the value of K. And let's use experiment 1. So K is going to be equal to the rate 2.52 times 10 to the minus -4 divided by 2.00 times 10 to the minus 2 multiplied by 1.20 times 10 to the minus 1 multiplied by 8.00 times 10 to the minus 2. But this time, this is squared because it's second order, and we'll use double brackets. And putting all that into the calculator, be very careful as you punch this into the calculator. Use brackets, use double brackets even. This gives us 16.4. We give answer to 3 sig figs. And the units is asking rate and determine the rate constant as well. You usually always give the units. So if you look here, we've got concentration, sorry, we've got the rate over concentration times concentration squared. So that is moles per decimeter cubed per second over moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed squared. You see, that cancels out with this. And so you've got s to the minus 1. If you look at these over here, this will be mole cubed, but you're dividing by mole cubed. So it's going to be -3. And you're dividing by dm to the -9. So it'll be dm minus -9, which is 9. And that wraps this question up, ladies and gentlemen. See you next time.